Welcome. In this video, I'm going to go over solutions for the problem set for A and B. So this will be a little bit longer, a few more problems than part 1. 7a says, explain what is meant by the atomic radius of an element. An atomic radius is what it sounds like, but it's a little bit more involved than that. So atomic radius basically describes the size of an element. So it's the size measured from the center of the nucleus to the edge of the cloud but here's the caveat of a bonded atom. Okay, because bonding is going to influence where the boundary of that cloud is, as well as being helped to define it. So often what they do is actually measure from the center of one nucleus to the center of the next. So like if you have a diatomic element like Cl2, you can measure between the two nuclei and divide it in half, and that should be your radius of each atom. So then that rolls into part B1. The atomic radii are given in the data booklet. Explain why no values for atomic radii are given for the noble gases. And B, the reason for that is because no bonding means no measurement according to the definition. It's not that they don't have a radii, we just don't have a way to measure it consistently in the manner that other atoms have their radii measured. And then 2, describe and explain the trend in atomic radii across the period 3 elements. Period 3 elements, this was part 1, period 3 elements, like any period, decrease across because the effective nuclear charge is increasing, but the energy level, or N, remains the same. So you're not adding any new energy levels, no new floors for the electrons to go into. So even though you're adding more electrons, they're just going into orbitals already there. But the effective nuclear charge is going up by 1 every element that you move over. So that's going to pull the electrons in tighter, making the radii smaller. And then number 8, says Si4 plus has an ionic radius of 4.2 times 10 to the minus 11th, but Si4 minus has an ionic radii of 2.71 times 10 to the minus 10th. It says, explain the large difference in size between the Si4 plus and the Si4 minus. So what they're getting at here with number 8 is that Si4 plus has lost 4 electrons. So its configuration now is Ne, and that's it. It's full, 2 floors. Okay, so energy level 2 is as far out as it goes because it's lost the 4 electrons that were in the 3s2 and the 3p2. Whereas Si4 minus has done just the opposite. Si4 minus has gained 4 electrons, and it now has a configuration like argon or the 3rd energy level. So Si4 plus has emptied out the 3rd energy level, while Si4 minus has filled up the 3rd energy level. So that's the huge difference in its size, is it's a difference of an energy level. Number 9, which of the following is a property of gaseous atoms? Ionization energy, yes, that's defined as removing electrons from a mole of gaseous atoms. Electron affinity, that's also defined in terms of gaseous atoms. Electronegativity, this one, not always. This is the attraction for a bonded pair of electrons. So this could be in a solid or a liquid as well. So it's not that it can't be in a gas, but it doesn't have to be in a gas. So A, just 1 and 2 have to be defined as the property of a gaseous atom. Number 10, which of the following changes is endothermic? This one is difficult, but what I do want you to realize is when you look at number 1, you see that an electron's being lost, or it's being ionized, and losing an electron requires energy. So this one's going to be endothermic. But then when I look at the second one, and I see that it's gaining an electron, that then has to be exothermic. These are opposite processes, so only one can be endothermic. So then it looks like, well, just one should be my answer. Well, strangely enough, if you look at this one's already an ion. So if I gain a second electron, that actually becomes endothermic as well. And that's why it's weird. I don't expect you to recognize that 3 would be an endothermic process, but you should definitely realize that losing electrons requires energy, gaining electrons releases energy. So that would be the takeaway from this one, and the correct answer is B. Number 11, identify the element which is likely to have an electronegativity value most similar to that of lithium. So if I look at lithium, hydrogen is right above it, so that seems like that might be similar, although lithium is a period down, so it's going to require less energy. It's going to be larger and looser than hydrogen. And hydrogen only has the 1 electron, so it seems unlikely it's actually going to give it up. Beryllium is right next to lithium, so it's going to be smaller and tighter. Sodium is just below, so it's going to be looser. Magnesium is actually kitty corner, so if you're not looking at periodic table, you have lithium with hydrogen above, unlikely to lose. Beryllium, a little tighter over there because it's a little smaller. Sodium, a little looser because it's down below. And then I have magnesium, which is, it's a little tighter moving over than sodium, but it's going to be a little looser because it's down a level from lithium. So C would be most likely to have the similar value because it's moving to the right where things get tighter, but it's also moved down, making it larger. So in the wash, it's likely to be magnesium. Number 12 has a graph here, and if you look, you'll see that BE, MG, CA, SR, and BA are going down the period 2, or down family 2, group 2. They want you to identify the properties. So it's a property that's decreasing. And A says ionic radius. Well, they would all pick up a +2 charge. So ionic radius is actually going to increase because you add an energy level as you move down. B, atomic radius, same situation, it's going to increase. C, neutron to proton ratio, decreasing down. Not sure on that. I'd have to do some math, but it seems to be, 1 to 1 or pretty close to it. So let's look at D, first ionization energy. That one's definitely going to decrease because as the atoms get larger going down, it's going to get easier to take electrons away. So first ionization energy will decrease all the way down the family. Number 18, atomic radii and ionic radii are found in the IB data booklet. So they want you to explain 3 different things here. So taking a look, A says the potassium ion is much smaller than the potassium atom. Well, K versus K plus is going to be, this is going to have 4s2 as its last, sorry about that. This could be 4s2, whereas this is going to take on just argon, or level 3. So you empty out a complete energy level, you empty out the 4th floor, so it's going to get much smaller when you lose that electron. B, there is a large increase in ionic radius from Si 4 plus to phosphorus 3 minus. And again, the difference is Si 4 plus has emptied energy level 3, whereas P3 minus has filled energy level 3. So it's a difference of an energy level creating that huge difference in ionic radius. And C, the ionic radius of Na plus is less than that of F minus. Well, if I look at Na plus has the configuration of neon, and fluorine has the configuration of neon. So the electrons are arranged the same way. So why is it that Na has got a smaller radius than that of F minus? Well, if I look, it's because Na has a plus 11 nucleus, whereas fluorine has a plus 9 nucleus. So even though you have the same electrons, you have a stronger nucleus pulling those electrons in, slightly tighter with Na and not quite as tight with fluorine. Number 14, explain why sulfur has a higher melting point than phosphorus. So if I find phosphorus, it's in family 15, and sulfur is in family 16. And so when I look at kind of typical bonding form, typically sulfur exists as S8, whereas phosphorus exists as P4, and they're both covalent bonds. So it's not like one's got an ionic bond and the other's got a covalent or a metallic bond. They're both nonmetals bonded to themselves with covalent bonding. But because they're covalently bonded, then they're going to be nonpolar because, again, they're bonded with themselves. So there isn't going to be much for intermolecular forces. So it's really going to be the temporary dipoles or the dispersion forces that can hold it together. So really, it's a matter of who's going to have more opportunity for temporary dipoles or dispersion forces. And because sulfur has 8 bonds versus the 4, there's going to be a lot more electrons, more bonds equals more chance of temporary dipoles and dispersion forces developing. And more dispersion forces will hold it together more tightly. Number 15 wants to know which physical property generally increases down a group but decreases across a family. So it increases as I move down, it increases. As I move across, it decreases. So it increases. Melting point, not consistent, varies with metals versus nonmetals, so that's not going to hold true. Electronegativity actually decreases down and increases across. Ionization energy has the same trend, decreases down and increases across. It's atomic radius, or D, that increases down as you add an energy level, but decreases across as the effective nuclear charge increases. Number 16 asks, the elements in the periodic table are arranged in order of increasing atomic mass, radii, nuclear charge, or ionization energy. This one's a little bit tricky because technically they're arranged according to atomic number, but atomic number is equal to nuclear charge because nuclear charge is determined by the number of protons. Number 17, what is the order of decreasing radii for the species Cl, Cl+, and Cl-? Well, Cl- is going to be the largest because Cl- has gained an electron, and so the electrons are going to repulse each other a little more and spread out slightly compared to Cl. And Cl is going to be significantly bigger than Cl+, because now you've got fewer electrons repelling one another. So that would be the correct order. Number 18 says, which one of the following elements has the highest electronegativity? Well, electronegativity is going to increase as atomic size decreases, tiny and tight. So when I look at these 4 elements, chlorine is the smallest of the 4, closer to the upper right corner, so it should have the greatest electronegativity. 19, which properties of the period 3 elements increase from sodium to argon, so left to right, and I've got nuclear charge, atomic radius, and electronegativity being listed as my choices. Well, nuclear charge increases, atomic radius increases. I'm sorry, atomic radius decreases. And which is why nuclear charge increases is the reason atomic radius decreases, and electronegativity then also increases. So C would be the correct combination. In 21, they use a fancy term called isoelectronic. Iso just means same. So like if you isolate something, you keep it in the same position, don't let it move. So, when we're talking about isoelectronic, we're just talking about atoms that have the same number of electrons. So Cl minus, K plus, and Ca2 plus all have 18 electrons like argon. So the question is, what do the ionic radii look like? Well, Cl minus is in family 17, so it has an effective nuclear charge of, 17. K has 19 protons, and calcium has 20 protons. So same number of electrons, same arrangement of electrons, but change in the strength of the nuclei means calcium's going to be the smallest, chlorine's going to be the biggest, so B would be the correct graph. Number 5 says the x-axis of the graph on the right represents the atomic atom of the elements in period 3. What could represent the y-axis? A, melting point. So I see it increase to family 4, which that would make sense. Metals, it increases as you have more valence electrons for the sea of electrons. Family 4 can make those giant covalent structures, and then it plummets when I get to the weaker covalent bonds with just dispersion forces. B, electronegativity. No, I'd expect that to increase pretty linear across. Atomic radius, I'd expect the opposite. I expect it to decrease pretty linear. And ionic radius, I would expect it to decrease, and then when it reaches the negative ions, have a big jump up and then decrease again. So A is the one I'd expect to have this shape. C, the best definition of electronegativity. A, the energy to gain an electron, gaseous atom to gain. Doesn't have to be gaseous. It's not actually gaining, it's attracting a bonding pair. So B, the attraction of an atom for a bonding pair of electrons. That sounds pretty good. C, the attraction between the nucleus and the valence electrons. That's not electronegativity. And B, the ability to attract electrons from another atom. That's actually electron affinity, the ability to take them. So when you're looking at the attraction with a bonding pair, that's electronegativity. Number 8 asks for the definition, define the term first ionization energy. So it's the energy required to remove 1 mole of electrons, or to remove an electron from 1 mole of a gaseous element. B wants to know why the first ionization energy of magnesium is higher than that of sodium, and that's because magnesium has a greater nuclear charge, effective nuclear charge, and therefore a smaller radius. So it's got a greater attraction for its electrons. And number 10A says outline 2 reasons why a sodium ion has a smaller radius than a sodium atom. And it's going to have the same effective nuclear charge. So that will be a non-factor, but it's one of the reasons that they want you to include, even though it's a non-factor. But the big reason it's actually smaller is sodium ion, Na+, only uses N1 and 2, whereas Na uses N1 through 3. So you empty out that top floor, but you have the same nuclear charge, and Na plus will be the smaller one. So those were the two reasons they're looking for. Again, to me, that's really more of just one reason. B, explain why the ionic radii of P3 minus is greater than the ionic radius of Si4 plus. I'm pretty sure we've explained this earlier, but Si4 plus is going to have a configuration equal to neon, or 2 full floors, whereas P3 minus is going to fill up the third energy level and have a configuration to argon, or 3 full floors.